Okay. Now I'm gonna explain about the distribution. So in general, we can divide distribution into two big forms. The first one is discrete distribution, and then the second one is continuous distribution. So what is discrete distribution? Discrete distribution can be defined for everything that is a list. For example, discrete distribution can be expressed, I'm going to state this, can be expressed in a list here. On the other hand, for continuous, it cannot be expressed in a list. Okay. What's the example? For example, in a room, in our house, for example, we have family consists of our father, which represent first person, or mother, which represents second person, our sister, third person, and us and ourselves. So this is the third person. So this is the list. You can make the list 1, 2, 3, and 4. On the other hand, continuous function cannot be expressed in a list. What does it mean? For example, I'm gonna give you the most common example. Um, for example, uh, we have time. Time cannot be expressed as a discrete function. Instead, time only can be expressed as a continuous function. Why? For example, you have 1, you have 2, you have 3. So this is the time. You cannot say that. Let's say I run for 3 minutes. That's the probability that you run for 3 minutes is equals 0. Why? Sorry, x equals 0, because when you said you're gonna run for 3 minutes, then there are too many possibilities that you can include here. Okay, for examples, you might say that could be 3 minutes 221 second, or maybe it's 3 minutes 0.273 second. So there are too many possibilities. So that's not the correct way to express the discontinuous function. Instead, you have to express it in the range or in the interval. So you have 2.8 x, for example, here, and then 3.1. So that's how you exactly define the continuous function. Okay, and then when we use continuous function here, you also need to keep in mind that the notation using greater than, less than, equal is actually the same with the a with or less than, greater than this sign. So this is exactly what you are trying to keep in mind, because sometimes you might confuse if I cancel these, then is it going to be the same? But it turns out it's the same. So this is the distribution, and you have discrete and continuous here. So how so this is the first, sorry, this is the first introduction about the distribution of this. And then in distribution, there are also terms that we usually encounter. So another terms to express the shape of our distribution. So here we have discrete first, discrete, okay, and then here we have continuous, okay, and then for discrete distribution, we have this probability mass function, or usually we say PMF. So this is the common abbreviation used to describe the probability mass function. In continuous, we have this probability density function, or PDF here. And then both PMF and PDF, we can also define the cumulative of distribution function, or the abbreviation of CDF here. Okay, so what exactly CDF here? So CDF, okay, um, it's essentially the area under the curve. So we need to calculate the area under the curve from CDF. But both PMF and PDF, it simply tells us the shape of our function. Okay, so this is just tells us the shape of our function. So it could, for continuous, for example, it could be uniform, it could be exponential, or it could be normal, which we known as a Gauss distribution. And so that's the distribution that we want uh, to know. And for this, for example, here I will explain you about the discrete first. For discrete distribution, here, then for discrete distribution, for example, uh, we have a dice. Okay, so a dice which is 6 sides. Okay, so we know the probability of a dice is always 1/6, correct? And then we can make the graph, the bar graph here that represent our this is the outcome, And this is the probability here. And this is the 1 per 6 here. And then this is our first, for example, first, 2, 3, 4, 5, and 6 here. And then this is our, I'm sorry, I have to move it here and here. My bad. Not this. Not this. Okay, this one here, here. So, so this is the probability mass function for discrete, and you have to understand here that it's equal because in discrete, yeah, this is this. If you see the flat, the flat bar here, then it's totally tells you that it is discrete function. And then in a cumulative form, sorry, so we have, I forgot to, this is the PMF, and then the cumulative form of it, cumulative distribution or CDF, will look like this. So you have this value, I'm gonna scale this, okay, probably I'm gonna, oh no, I'm gonna make new graph here. So this is what we'll tell you here. Wait, here I have 1, 2, 3, 4, 5, and 6. So this is the, yeah, so this 2. Okay, so this is the cumulative distribution function from this grid function here. So this is what we have. And then you have to keep in mind here that this has to be 1, okay, because it's impossible uh, if you throw a dice, then will give you 5 per 6 as the total of the probability of throwing a dice. So this information tells us, for example, if you want to know this bar, then the way we express it is like this: probability of x less than or equal to 4 is basically the summation of probability of x equals 1, which this plus probability x equals 2 plus probability of x equals 3 and plus probability of, can make this fit here, x equals 4. So this is what you really have. Okay, so this is the discrete distributions. And how about the continuous? How about the continuous distribution? So for continuous distribution, let's say we have this bell-shaped curve. For example, we want to measure the height of a woman. So we have this curve, which is height here. Okay, we have this curve. Okay, perfect. And let's say this is 145. It doesn't matter the value, just for presentation. So we have this, and then this is the probability density function, and this is the cumulative distribution function, what you will get from here. I'm gonna copy paste this here. For probability for cumulative distribution function of a continuous distribution function, then you will have this subcurve. Okay, it's not perfect. I can make it better. Okay, this one. So what basically tells you here, so in order to get CDF, so CDF is actually the area x to the left of the PDF. So for example, if you want to know what CDF here, for example, this is, let's say this is phi. Okay, what is phi, for example, and then you draw it here. It simply tells us that this area, for example, this is 2.5, then phi equals to 2.5. So this is the relationship between PDF and the CDF in continuous distribution function. I will explain more about this. For example, we have this wait, I'm gonna give you, for example, we have this uniform distribution, sample one. So uniform distribution will give us this kind of graph. So you have this, for example, this is the fx, okay, okay, here, and this is the x, a, and b, okay, and then the CDF, since I mentioned that CDF is the area from x to the point A here, so this is the CDF of PDF. This is PDF graph, but we want to find CDF, so CDF is this area, so it's best multiply with height, this height, and then so this area to the left we can denote as AL, A sub L here, so AL, A sub L equals to B H, okay, so best multiply with height, in which this is x minus A, x minus A, multiply with our function fx. So basically, we know the function here, for example, for uniform distribution, fx is equals to 1BA. Okay, this is the function for uniform distribution. Hence, you will get this AL equals to x minus A, 1B minus A. So this is exactly the AL. So you can express this in mathematical format where A sub L equals to probability of X capital less than the some number here equals to X minus A divided by B minus A. So this is the CDF for uniform distribution function. Another thing that that we can explain here, the exponential, for example. This is the exponential distribution. here we have this curve of exponential distribution. So we have this, for example. Okay. So recall the fx equals to is the weight parameter multiplied with e to the power of weight parameter multiplied with x. So this is the fx function. And then we want to find the CDF, as mentioned before. CDF is the area to the left of some values x of our PDF. So CDF is the area to the left. So for example, we take this x, x here. So we have probability of x to the x less than x, meaning this is gonna be 1. Okay, let's say this 1 minus this e minus to the power of wake x here. So this is the CDF of this our exponential distribution. Okay, so let me ask you a question. What if we want to find the area to the right here? What does it mean? This is the area to the right. What if we want to find this? Okay, so if we want to find area to the right, so it's simply 1 minus AL, meaning area to the right is 1 minus 1 to the power of wake x equals to 1 minus 1. This can minus cancel each other, so we have e to the power of x here, so equals to e x here. So this is what you really have. This is not, but one thing one must not must keep in mind here that this is not CDF because this counts to the area to the right. So it's just in case you want to calculate area to the left here. Okay. So that's the concept. And then what if we want to calculate the middle area, for example? What do you mean middle area? So I'm gonna move this graph. I'm gonna move it here. So what if you want to sorry. So what if you want to calculate this? This is A and this is B, so you have this correct. This is, you want to find this A equals to P, probability of A less than X than B. So it's going to be equals to P, X less than B minus probability of X less than A, correct? So what does it mean? So that means P here will cover the entire, I'm sorry, if, okay, P probability of X less than A will cover this area, correct? And then probability of X less than B will actually cover the entire area of this. So if you subtract probability of X less than B with probability X less than A, then you're gonna get A. So that's the idea here. So we have here probability of A here, XB equals to 1 minus E minus to the power of Y parameter multiply B here, 1 minus A here. So you will find, so this is what you have, correct? Okay, so I think that's the concept of PDF, CDF in both discrete and continuous distribution. It's very essential because once you understand the concept, then it's gonna be easier for you to understand depth about this particular topic. There's also a topic that I want to explain, but I think we're gonna jump this real quick. Well, I don't want to explain too much about it, which is the normal distribution. So normal distribution is common and one of the most one of the most famous, I would say, distribution, uh, continuous distribution. So, what's the point? 7, 2, 7, 2, 1, 7, 2. So this is okay. So this is the yeah. So example 3 here is the normal distribution. Okay. So normal distribution technically has this shape. Okay. So this is the normal distribution, and you will have this bell shape curve. It's pretty much similar. Yeah, it's similar with this one. This is the normal distribution actually. Okay, so but you have to know one thing, that this function, we're gonna use it often uh, in the subsequent video, because I'm gonna explain a lot about the relationship between linear regression and Gaussian distribution of normal distribution. Uh, so the function here can be expressed as 1 per 2p standard deviation multiplied with e 1 per 2 x square here. So this is the function, normal distribution, but usually we're gonna write this as follow. So this equals to normal. This is the p, and this is the standard deviation. That's the way to express it. So I think that's all for today. Uh, Next, we will delve more into the covariance, variance, joint distributions, marginal distribution, and see you in other videos.